Hi, I'm Jim Heppelmann, the CEO of PTC, and I'd like to share with you some thoughts about digital transformation in manufacturing that I recently shared with the National Association of Manufacturers in Washington, D.C. So let's dive into digital transformation. And I'd like to start by saying I don't think this means becoming a digital company per se, but it really means looking at all the different ways that new digital technologies could transform an industrial company. And before I go deeper, I want to just point out that a tremendous amount of money is being invested in this topic of digital transformation. In fact, the industry analyst firm IDC did a study in 2018 that said on a worldwide basis, $1 trillion was being invested under the heading of digital transformation. And the report went on to say that 30% of this investment was coming from both discrete and process manufacturing. So that's basically $300 billion that your peers are investing in digital transformation. And so if we're going to invest $300 billion, we must be expecting to get even more than $300 billion in return back. And so I want to spend a little bit of time too saying, well, what is the nature of that return? What could you expect to get? And I think at the highest level, to be simple, it's efficiency. A company that operates more efficiently in everything it does. It's differentiation in the products, in the brand promise, in customer service. And then finally, flexibility. The type of flexibility that allows a company to adjust its strategy, to changing dynamics in the industry and to do that quickly. So there's some very big returns. And I want to point out, I think for an industrial company, there are three unique levers that you have that could be used to transform your company. So the first is products. You could actually change what it is that you produce by looking at digital technology. The second is operations. You could be more flexible, more efficient, higher quality in terms of all your processes in production, supply chain, what have you, using new digital technologies. And the third is actually people, your workers. Your workers could be made much more productive thanks to several new digital technologies that are coming onto the scene. So you have these three different levers, and I'm going to talk about all of them, but I'd like to start with the discussion about how your products might change. Now, in a lot of cases, people are producing products that are physical, and perhaps over time they're becoming a bit more digital. I want to start by talking about the physical part of products and then the digital parts. So here's a traditional physical product, a fantastic looking snowmobile from Polaris, and I want to talk about how high-performance computing, which is one of the new capabilities available to us thanks to the cloud, is used to transform the way we would design such a product. So let's take a quick look at a video. This snowmobile has a certain part in its suspension that I'm fixated on. It's kind of rainbow colored right now to show the levels of stress and right now deformation. You can see that under load, this part's going to move around a lot. And if I look, there's some stress pockets here that are concerning. It's likely to break. So I've used analytics to simulate what will happen to that part, but now I can simulate it on each change. So I'm going to insert here some extra ribs, if you will, in this aluminum extruded part. And as soon as I commit that change, using high performance computing, we reanalyze that part, and I can see immediately that the problem's been solved. So now think about it. With high-performance computing, I can simulate on each and every mouse click, basically, or certainly each and every change as I'm designing a product. I never get far off track because I have analytics in high-performance computing looking over my shoulder at the type of work I'm doing and guiding me each step of the way, whether each change I'm making is adding value or perhaps subtracting value. Next, I want to talk about artificial intelligence and additive manufacturing through the lens of design. But before I do that, I want to show you something to think about, and that is how Mother Nature designs things versus how man designed things. So here's a quick little video clip thinking originally about a flying machine. That's Mother Nature's flying machine on the left and man's flying machine on the right. And if you look at the wing, the external, it's very, very different. And if we look at the internal, the ribs and struts and so forth, very, very different. Lightning strategies, again, very, very different. Mother Nature makes very sophisticated designs using a additive process called cell division. And it yields very different solutions, for example, for capturing energy or for circulating fluids and gases and so forth. Mother Nature systems on the left is extremely sophisticated and frankly extremely efficient. Man's design on the right is trying to approximate that to the degree possible, but constrained by what we can actually produce. So, for example, the veins and arteries coming out of the hearts have wildly variable diameters. That's pretty hard to produce. So in man's machines, much more of constant diameter piping and so forth. So what's interesting is that if we use AI and additive manufacturing, we're no longer constrained to the limitations of traditional manufacturing processes, and we can get much closer to designs that really look like maybe Mother Nature created them herself. So I want to show you a quick example. And for this example, I'm going to use an iconic Triumph motorcycle. Now, a Triumph motorcycle, is a special product, and of course the cosmetic look and feel of this product is very, very important to the buyer. So I'm going to say, how could I radically change the design without making it look strange? Because probably if it looks strange, people wouldn't buy it. And I'm going to use a strategy of AI-driven generative design on the front end and additive manufacturing on the back end. And I want to focus on a certain part, what's called a swing arm. It's the part that attaches the rear wheel to the motorcycle. It's a normal assembly made of steel castings and steel pipes. It's 5 parts when modeled in a CAD system. That's what it looks like in traditional manufacturing. So now I want to switch to AI and additive, but I want to specify what the outer envelope looks like and then turn the computer algorithms loose. So I say I want it to look like that outer shape, but you figure out what to put inside it. You don't have to make it hollow or make it solid. You can make it as hollow as you want, but make sure it works. So the blue elements here are really the areas that are calculated to carry meaningful load in the part. So you can see that's actually the efficient internal shape. Very, very strange shape, very strange looking. And so by the time the CAD system regenerates this part with the human-specified outer shell and the algorithm-driven inner shell, I end up with a part that's really very interesting. It looks nice to the human eye, but look at the yellow shapes inside that human-specified outer shell. It's very, very elegant, interesting design. Looks like something Mother Nature might have come up with. And it's a very efficient design. It will print as fast as possible, consume the smallest amount of material, weigh the least, and yet effectively carry the load. Realizing, of course, that the load is asymmetric. There's a chain on one side, not on the other, and that's why the internal shape of the part is asymmetric as well. So kind of a great example of collaborative design that's part human, part artificial intelligence, and in both cases, back-ended with additive manufacturing, because there's no other way that you could produce such a part other than to print it using, in this case, a metal form. Now, switching from the physical part of products that are affected by digital transformation to the digital part of products, I mean, this is a profound story where more and more of the value of a product has become digital over time. This is an example inspired by John Deere of a tractor that maybe 30 years ago was purely mechanical. And then in the next phase, software came into the engine, software came into the cockpit. Then they realized we could connect such tractors to the internet and track them, monitor them, optimize them. At the next level, we could actually have tractors share information with other pieces of equipment, and we could have a whole system of equipment that work together. So for example, the harvesting equipment, the combine, if you will, could keep track of how much production we're getting from different areas of a large field, and that data could inform the fertilizing and planting strategy the next spring. So for example, we might put more fertilizer where production was low and less fertilizer where production was high. And we might put the fertilizer in a narrow band, knowing that in the next pass, we can land the seeds right within that band. Therefore, we'll fertilize the seeds and we won't bother fertilizing the weeds in between the rows. That's the kind of value, much more output, much less input that can be created by smart connected products sharing data with each other. Now, if you take that strategy to the next level, you get this so-called system of systems, where a tremendous amount of digital information is shared between dissimilar things. So for example, the tractor system, the equipment system I bought from John Deere might share data with a seed database, with a weather prediction system, with an irrigation system, to produce a smart farm. The difference here really is this is a very heterogeneous combination of things working together in an operation, and that's why we at PTC tend to call this smart connected operations. Now, smart farms are one example, smart cities are another, but of course, perhaps the best example is smart factories, because almost every factory has a lot of automation equipment that is connectable, but is coming from many different suppliers, depending upon the nature of your manufacturing. But by connecting it together, we can create a lot of value. The point of this slide really is that products themselves have begun to incorporate tremendous amounts of digital technology, now including connectivity and data gathering and analytics and applications built on top of that, all thanks to the industrial Internet of Things. If you ask, well, why would I do that? What new values do I get by putting all of this digital content in what used to be physical products? Well, there's a sort of stepping stone of value that could be created. At the first level, I can monitor the products. I know where they are. I know what they're doing. I know how often they're used. I know what environments they're used in. That data by itself can create a lot of value. At the second level, if I begin to think of this as a bidirectional exchange, I can actually gain control, remote control, if you will, of any type of product. And if I go to the third level, I could put algorithms in that control loop that would optimize things. So, for example, optimize the placement of seeds according to the previous placement of fertilizer, which was optimized according to last year's production level. And taking it to the final level, I can think about giving products full autonomy to make their own decisions. And of course, we see that in automobiles and frankly, even in tractors as well these days, and many other places. So the point is, digital content, especially once we've achieved connectivity, represents a tremendous value add and really fundamental rethink of product value propositions. And that's, in its own way, very transformative to an industrial enterprise. Let me give you a couple examples of that. Colfax is a company that I know well. They produce, amongst other things, welding equipment, the ESAB welders. They might get used in a factory. They might get used out in the field to do repairs. They might be used in some type of a cutting or fabrication process. They might be used in a custom shop. They might be used in a construction process. So lots of different applications, and if I could gather data from all the welders and all the different use cases and grab the amps and the voltage and when it's used and how it's used and frankly when it didn't work if there were a problem, I could very much optimize the design of that product, perhaps the production process. For sure, the customer support and service processes could be significantly optimized across a big fleet of very different welders coming, in this case, from the company in the ESAB brand. Let me switch to a different example. Otis. Otis has a strategy called Otis One that connects hundreds of thousands of elevators and escalators back to a central system, again, where they can be monitored. Predictive analytics can be used to determine when service would need to happen and to send service technicians out, fully ready to solve the problem when they get there. Another great example is Trane. Trane produces heating, ventilating, and air conditioning equipment. So these kind of units that you might see on the roof of a building. Now it turns out these units end up everywhere. I'm sure you can find them in every city, in every state, and probably around the world. But there are wear parts in products like this, and sometimes there are problems that need to be serviced. So what Trane found was that there was a tremendous opportunity to make spare parts management much more efficient. So for example, if I don't have any data about where the units are, how well they're working, then I need to have a lot of inventory of spare parts, because if any unit in any city goes down, I need to fix it quickly. I mean, keep in mind these things only run when you need them to run. And if you need them to run and they don't run, somebody's getting uncomfortable. So the strategy can move with a little bit more data from lots of parts everywhere to ample time to stage a part in the right place. If I had a few days or weeks to predict when a unit would go down, well, then I could have many fewer parts in a central inventory and ship them to the location just in time. So Trane, for example, had a tremendous payback on a spare parts optimization project, informed by Internet of Things type of data sources. So reflecting then on the product part of this discussion, I talked about high performance computing, artificial intelligence being used to drive generative design strategies, additive manufacturing giving you tremendous flexibility in the design, and then of course industrial IoT creating significant new ways to generate value and differentiate products. So this is a collection of new digital technologies that I think are very transformative to the products of a manufacturing enterprise. So let's move on then to operations. So how could a company change their operations sort of independently of whether or not they change their products? Now, if we drill into that, first of all, there is no shortage of technologies involved, for example, in the manufacturing processes of industrial enterprises today. At the lowest level, using this ISA 95 model, you'll find sensors and PLCs. And at the level above that, you'll find human-machine interfaces and SCADA systems. At the level above that, you might find manufacturing execution or manufacturing operation systems. And of course, at the level above that, you'll find enterprise business systems, ERP, supply chain, even PLM. So there's lots of data out there, but there's kind of two main problems. Number one, these are silo systems. They all have part of the data, and they don't do an effective job sharing it with each other. And the second problem is they don't actually have all of the data. There's a lot of data in other places that we really would need to get the full understanding of what's happening in a factory such that we could optimize it. So even though progress has been made, the system could be optimized to a much greater degree. And that's really where the notion of industrial IoT comes in and is applied in the smart factory setting. So the first thing that an industrial IoT system does is it taps into all the existing sources of data at level 1, 2, 3, and 4. But the second thing it does is it taps into non-traditional sources of information. Lots of new sensors can be placed throughout a factory to, measure heat, vibration, humidity, noise, whatever you want. And that picture can be integrated. We could get data from external systems that are measuring, weather or many different sources of potentially interesting information. We could get information from trucks that are moving throughout the supply chain. What do you contain, and where are you, and how soon will you be here? And we could get information from, other supply chain systems and so forth. And by integrating this all together, connecting, aggregating, and then using analytics to help us understand this data, we can really change what's happening in a factory. We can do much better asset performance management, make sure machines don't go down unexpectedly. We can do much better operations performance management, make sure that all lines run like our best line. And of course, we can do many other types of optimization delivered through new applications that are role-based and real-time and predictive and very flexible as well. So many companies around the world now are bringing in industrial IoT technologies and wrapping and extending their existing systems with a new layer of digital technologies. Here's some examples. The company Rockline, which is a good customer of our partner Rockwell Automation, was able to instrument and connect 5 different lines, if you will, and drive OEE up by more than 20%, simply by getting a better understanding of what's happening such that it could be further optimized. So a 20% increase in OEE is a very big payback in this type of industrial environment. Or the company Woodward. Woodward produces many different parts that you might find used in aircraft, a lot of different aircraft systems, engine control and monitoring systems, a lot of different components, but also equipment you might find used in wind turbines, in automated production lines, and so forth. And so in this case, it's not about tracking the products, it's about tracking the factories that make the products. And Woodward's done a good case of using industrial IoT and analytics data to be able, for example, to compare all the different factories to each other. So sort of internal benchmarking to understand where there are further improvement opportunities. Another great example comes again from Rockwell in the form of Arkansas Steel. And Arkansas Steel, of course, has continuous improvement processes, as you might expect. But what they found is that it was so hard to get all the data when it required humans to go out and measure and collect and aggregate and analyze this data. By instead placing, sensing and PLC systems and then gathering the data automatically, they were, for example, able to drive yield up by 3%. Now, a 3% increase in yield really does move the needle quite a bit. So it's another great story about industrial IoT. So thinking about operations, I mentioned industrial IoT. I mentioned artificial intelligence and analytics being applied to process automation. These are strategies that really do move the needle for manufacturing companies. So the last thing I want to talk about is people. Now, manufacturing enterprises have a lot of people. And maybe a strategy in former years was to bring in more automation so that we didn't need as many workers. But I think in every case, there remains a lot of workers because there are many problems that are much easier to solve with people than with automation. Now, what if we could make people much more productive? So I want to start by saying there's a very large problem here, actually, that needs to be solved. There was a study done by the National Manufacturing Institute, which is part of the National Association of Manufacturers, in conjunction with Deloitte, and it's been updated a few times. But their latest conclusion was that by 2025, there will be about 3.5 million production workers who have retired and only about 1.5 million who have been recruited to backfill them. And there's a couple of big problems. One is it's hard to convince new workers to go into what they see as low-tech jobs. And the second problem is it takes a very long time to train such a new worker, many weeks and actually many months. And so it's hard to get them, hard to train them, fair amount of turnover these days. It's a big unsolved problem. Now, there's a lot of companies throwing money at it. You know, Boeing, for example, announced a $100 million program to train new workers. And Boeing's spending $100 million because they're having trouble keeping up with their order book on the production line. And it's a shame, really, if you're successful selling airplanes, but not successful making them fast enough to keep up with the order book. That's a very expensive problem worth investing in solutions. Or in a much smaller environment, Lincoln Electric is spending $30 million to train new welders and to make the existing ones more skilled. So again, if Boeing's spending $100 million and Lincoln Electric spending $30 million, this is a problem worth solving. So how could we solve it? Well, I want to use this little 2x2 matrix to sort of help you think about where the problem lies. And what it really shows on the y-axis is where are the workers we're talking about? And on the x-axis, what is the nature or the type of work that they're doing? And what you find out is that in the lower left, or the lower row, we're talking about knowledge workers, people that work behind computers sitting on or next to desks. And so for knowledge workers, we have a lot of computing technology, a lot of software, a lot of digital stuff. But when you go up to the top row, which I would call frontline workers, we're now talking about people who are working in a factory or people who are out on service calls. And how do we give digital information to them? And turns out this is a lot more challenging. So in the upper left, if we're talking about factory or service workers who are doing fairly routine things, I suppose we can give them paper instructions, reduce digital down to paper, or maybe give them a mobile device. But what if they're out in factories or on service calls doing things that are fairly complex and variable? If you don't make the same service call time after time, but you're servicing different products that have different issues, and these are complex industrial products, computers and mobile devices and paper is not that useful. The thing is, in a lot of manufacturing enterprises, that's actually where the majority of the employees live. They live in the production and the service processes. Many companies have tens of thousands of employees doing this. And again, paper and mobile and laptops and desktops are not very useful solutions for them. What do we do? Well, I think the answer here is augmented reality, and I want to try to explain why. So first, it's worth looking at what is augmented reality. And augmented reality really means a set of technologies that allow you to take digital information and make it a natural part of the physical environment. Now let me drill into that a little bit deeper. So let's imagine there's a digital cloud, as there is, and it's full of impressive computing and analytics power and tremendous amount of digital data, which could be helpful to our processes, whether they're manual or automated. Now, if our processes are automated, we know how to plug machines directly into that cloud. And if you think about how much automation has changed in the last 30 years, going from paper little punch tapes to the kind of automation we have now, it's incredible amount of change that has happened in the last few decades. But let's think about how do we give digital information to humans? Actually, I'd argue that hasn't changed very much. I mean, I have an iPhone here, and when I think of my iPhone and how I interact with it, it isn't that much different from the first Macintosh I got from the same company 30 years ago. You know, that was an app that gave me windows of graphical and text-based information, and now I have a phone that runs apps that gives me windows of graphical and text-based information. So we really haven't advanced the capability of humans much at all, meaning that robots have benefited from the explosive power of digital to a much greater degree than humans have. And I'd like to take a little bit of a look at why is that. Well, let's think about a human. Unlike a robot, they do not have an Ethernet port. They have 5 ports, which are analog. They are the ability to taste things, the ability to smell things, the ability to touch and feel things, the ability to hear, and the ability to see. And I'd like to argue that actually the first 3, taste, touch, and smell, aren't very useful because it's very hard to encode digital information into them, and they're not very fast senses. Hearing is a bit faster, and then eyesight is lightning fast. I always say if you close your eyes, open for 1 second, and look around and close them again, and then think of how much information was ingested in that 1 second. It's amazing. You saw you're in a room and there's other people and things, and there was a window and it's a sunny day or a rainy day, and so much information you can hardly remember it all, but you brought it all in. So really the question is, how could we do a better job of leveraging these 5 senses when we give information to people? And I think the answer really is a modem. Now I'm joking a little bit about that, but when I think of a HoloLens like this, and then I think back to a modem, you know, if you're old enough, you know what modems are. It's actually an acronym or a contraction for modulate, demodulate. But a modem is a way to convert an analog signal to a digital signal and back again. And so we used to use that to send digital data from computers over analog phone lines and convert it back to digital signals at the other end so it could go into another computer or a terminal or what have you. But isn't that what a HoloLens does? Doesn't it take digital information and create things I can see and hear and therefore experience with my analog senses as if they're part of the scenery? And then furthermore, can't I talk back? Can't I say commands or make hand motions? You know, the famous hand motion is really an analog signal to a device that converts it to a digital signal and sends it back to the cloud. So as a human, when I put on such a device, it's like putting on a modem and directly connecting then to this vast source of digital information and computing power up in the cloud. So to help you better understand what this is all about, I'd like to start with a demonstration that normally I would run on a HoloLens, but for the sake of making it easier for me to show you, I'm going to instead run it on my cell phone. Let's take a look. So for this demonstration, I'm going to pick up my iPhone here and use it to show you what augmented reality looks like. And I'm going to run an app down here at the bottom, which is really a web browser that uses augmented reality, meaning it can see. So I'm going to open up a bookmark, and here's the demonstration we want to look at. And I'm going to select the first mode, which is what we call augmented reality. And then subsequently, I'm going to show you virtual reality. The application is telling me, hey, Jim, I'm looking for something shaped roughly like this. And from the outline, probably you can see it's a motorcycle. So as I come over and point it at this actual motorcycle, you see that it locked on and flashed yellow. Now, the yellow flash was really for your benefit to let you know that it's saying, I can see that motorcycle. And if we study that motorcycle for a minute, a very interesting thing is happening, and that is it is transitioning back and forth from the plastic motorcycle you see right now to the CAD-based motorcycle you see now, and then back to plastic and back to digital. And we show you that in a demonstration just to show you that when we see something real, we think also about its digital twin. And we can therefore take any information we have from the digital twin and put it onto the real motorcycle. So let's take an example of how that would work for sales and marketing. So I'm going to click on sales and marketing. And there's a couple of different examples of what we can do here with this motorcycle. So the first would be to show some of the key features. I'm trying to convince you to buy this motorcycle. So I've put some hot spots on the plastic motorcycle, and I can zoom in and touch those spots, for example, and learn about the engine. It's the 1190 RC8 engine, weighing only 62 kilograms and so forth. And I want to show you that that information is actually attached to the motorcycle. So even as the motorcycle moves, that information moves with it. I'm going to put the kickstand back down. I could also say, tell me about the front forks here, for example. And it tells me about the inverted forks, or, tell me about this hot spot on the back wheel. And it tells me about the powerful grip brakes. So that's an example of how I could use it. I could also say, bring me the spec sheet and just make it part of the scenery. So now I see the specifications in the background for this particular motorcycle. Let's switch gears and say, how might I use it as the operator? If I'm the person who purchased the motorcycle. Well, the first thing, and on the HoloLens, by the way, this would be a voice command. But the first thing I could do is say, show me what the sensors say. And it tells me that there's 2.4 liters of fuel in the fuel tank. And there's 78.1 now PSI in the back wheel, and 78.0 PSI in the front wheel, and 0.76 liters of, now 0.8 liters of oil in the oil pan in the engine. So this is kind of interesting because these would be sensors measuring things on the motorcycle, and then through IoT communicating that data up to the cloud, and I brought it back and added it to my view of the motorcycle. Now, what else could I do? Well, I could say, for example, show me how to operate the motorcycle. And if you look on the right side now, there's 1, 2, 3, 4. If I touch on 1, it says, here's the clutch lever. On the left side, it's fitted, it's hydraulic and self-adjusted. And oh, by the way, there's a tool set under the seat. And I want you to know that there's a handbrake on the right side. It operates the front wheel only. And number 4, don't forget there's an ignition and steering lock down here that you'll have to interact with. Now, finally, I might say, anything else I need to know, perhaps from a safety perspective? And it says, yeah, just be careful because these parts, the engine and exhaust system, get hot during operation. So please be aware of that. Now, let's take one other example. Let's say I'm the service technician. First thing I could say is help me to assess this product. Kind of like do a diagnostic x-ray, if you will, on it. And you see there's some parts kind of highlighted here in yellow on that swing arm. And I might say, okay, analyze what seems to be wrong with those parts. And I see that there is a swing arm deviation. And here's the analytical data around that particular problem. Then I might say, show me how I would repair it. And it gives me a play button on the right side. And if I press play, it says step 1 is to remove the rear brake calipers, which are down here, and the bolts are coming out, and then the caliper itself comes out. And then we see that step 2 is to remove that rear axle nut that's blinking and twisting off. And then step 3 is to remove the rear axle bolt. It goes out the other side. Step 4 is to remove the entire rear wheel assembly, and out it comes, and so forth. And then finally remove the fender and keep going. So hopefully that all makes sense. Now, what I want to cover is one last topic. That was augmented reality. I'm putting digital information on a physical motorcycle. But what if I didn't have the physical motorcycle? I'm supposed to work on it tomorrow, but I would like to practice. So in this case, I'm going to bring the digital twin down and place it on the table here. And you see that's the digital representation of the motorcycle. So let's say I don't have the motorcycle. We'll just set that aside. And I still want to understand what will I need to do to service it. Well, let's go into the service mode, and I would say, okay, step 1, assess it. And it says, here's the problem. And step 2, analyze the problem. And it gives me the same kind of data I had before. And then step 3, show me how I would go about repairing that. And again, the exact same procedure can be played against the digital twin. So what I can do on something real, I can repeat or proceed on something virtual using virtual reality. And these are very powerful concepts. Okay, so hopefully that demonstration was helpful in kind of putting the concept of augmented and virtual reality, in the forefront of your mind here, so that I can talk about how you might use it as part of your industrial transformation strategy. I want to show you one quick example that I'm going to refer to, and this is a company called Cirrus Aircraft, who produces, amongst other things, this new personal jet. And just to show you an example of how augmented reality is being used, this is the CAD model of the jet in an analysis package that was doing computational fluid dynamics. And here I've taken the flow lines off the CAD model and put them on the full-size aircraft. So the point really is I can digitally see things now, or I can see things that are digital that, if I take my smart glasses off, I can't really see because they're not really there. But it's information we have that's very, very powerful. And think about it here. I've been able to effectively create a wind tunnel with augmented reality, where I can take digital analyses and place them on physical products and really see what's happening, as that aircraft flies through the air, in this case, the air being simulated. So let's talk about the capabilities that augmented reality brings to the table. First of all, like that airplane, or like the fuel level in the gas tank on the motorcycle, you can visualize information that otherwise would not be visible. I can visualize sensor readings. I can have an entire human-machine interface on something. I can visualize flow lines of air around an inanimate object. So digital information becomes something that I can see and frankly, as well hear, as if it were part of the analog environment that I'm immersed in. The second thing is we can provide instructional content. I can show you how to start the motorcycle, or I can show you how to take the back wheel off. And I can do it step by step and even bring an expert in to join the session. So if you're struggling with the instructions, you could have an expert join the session and they would be able to see what you see and provide guidance to you, even provide guidance that shows up as digital content in the physical world. And then the third thing is I could allow you to interact with things by creating an actual, a virtual interface. For example, a spoken command. I could have told the motorcycle, start. And perhaps, the voice command start would have been sent up to the cloud and sent back down as a command into the engine that caused the motorcycle to start. So we can think about brand new ways to both get information from and provide information to physical objects. It's a very, very powerful concept. Now, when you bring virtual reality into it, it adds another dimension, because now, in addition to visualize, instruct, and interact, I can simulate. And so I showed you the example of I don't have the real motorcycle, no problem. I'll simulate a motorcycle and then visualize, instruct, and interact with it. So AR and VR really are siblings. AR is about digital information in the real world, and VR is about digital information in a simulated world. Both of them have a lot of applicability to manufacturing enterprises. Let me give you an example. Here's a quick little video clip of the retiring worker. So this first worker, wearing a HoloLens, is firing up a piece of software called Waypoint. A waypoint, by the way, is a 3D GPS coordinate, so it's X, Y, and Z. And he's doing what he always does, but he's recording his voice, he's taking pictures, it's all being videotaped, and then we're placing waypoints, 3D points in space to say this content lives here in space. So second of all, he interacts with the robot and captured that in a video and attached the video to a waypoint. Now he's pointing at a pliers and taking a picture of the pliers and attaching that and the voice commands to the pliers. And now he's coming over and using the pliers in another step to manipulate the bit, if you will, on the end of the robot. So he's recorded a whole process while actually doing it. So we had the expert do what he always does, but we have extracted the expertise. And now we have an author, an editor, if you will, tweaking it a bit, trying to make it a little prettier, perhaps a bit more succinct, and even printable if we wanted to print it in PDF. Now the new employee comes along, puts the HoloLens on and says, guide me through that procedure. And she says, I want to do the cobot test. And it says, okay, number one, reset the e-stop button, just like the expert did right here. First, she confirmed that was done, which is helpful to know. So step two is push back the cobot arm, just like that. And again, that instruction was attached to a point in space. And then she confirms that she did that. And then step 3 is come over here and grab this pliers right here in space, and she does that, and then confirms that this has been accomplished. And then step 4 is come back to the robot and manipulate the bit on the end of the piece there as shown. That's a great example of a retiring worker leaving his or her expertise behind in an AR format that we can pass on to somebody else and even see here how well did this person ingest this information. You know, how long did it take to do each steps? Should we tweak the steps a little bit, or are we happy with the performance time and so forth? So this is an example of AR solving this retiring workforce training problem that one gets when bringing in the next generation. Here's another example of AR being used by BAE in the assembly of batteries that are used in hybrid buses. So in this case, the worker, or workers, as you'll see in a minute, put on a HoloLens, and they're doing an assembly process. And you see the digital instructions floating in space right in front of her. So she's basically confirming, I did that step, and it says, okay, here's what you should do next. And so this particular procedure was authored from the engineering CAD data that was used to specify the manufacturing of the components, and now it's guiding her through the complete assembly to make sure she did everything just right and didn't make any mistakes or omit any steps along the way. So another very powerful example of using augmented reality for manufacturing instructions. Here's a fun example from a warehouse. So I put on my smart glasses, I'm a warehouse worker, I jump on my forklift. It says, do you want to do a pick request in the upper right? And I'm going to say yes. And then it says the next pick request scheduled is this one. Please confirm you're willing to do it. And I say, yeah, okay, I'll do it. And then it says, okay, well, go to aisle 17, shelf 3, and here is the bill of material that I want you to pick up for this load. So you'll see on the floor here an arrow that suddenly becomes a turn left arrow. And then right about here in this column, you should find the next parts that you need to add to that pick list. So this is a great example. Pick up the parts, maybe even scan the barcode there and place it in the order and move on to the next one. So this would be, let's call it AR-guided picking process, like one might find in a warehouse or a spare parts depot or something like that. Tremendous improvements in human productivity on the order of 30 to 50% can be gained by the use of augmented and virtual reality. These improvements are big enough that I think companies are beginning to ask, where should we draw the line on automation? You know, when should we automate with robots, and when should we make humans more effective? Now both machines and people have skill sets, and they're a little different, but now we have both levers to pull. We can either automate with machinery, or we can automate with better information being sent to people and take advantage of some of the human characteristics of flexibility and so forth, you know, in terms of different procedures and the ability to quickly move from doing one thing to doing another and so forth. Okay, so I reflected on digital transformation as it related to products, and I showed you some examples of how you could differentiate products, make very different products, bring in Internet of Things and analytics and artificial intelligence into products. I talked about how Internet of Things and artificial intelligence, again, play a key role in driving process efficiency. And then I showed you how augmented and virtual reality can really address human productivity, and in particular, the workforce turnover and expertise shortage that many people find in their vast number of production and service workers in their company. So I think you can see that digital transformation can unlock unbelievable amounts of value. And this is what companies are pursuing all around the world. They're thinking about the entire connected enterprise, the products, the operations, the workers, you know, sales and marketing. How can I use digital technology to really take the company to a different level? Not to become a digital company, but to become an industrial company that's far more efficient thanks to the power of digital technologies. So that brings me to an end. That's some good thoughts I hope you appreciate around digital transformation. Lots of opportunity here, lots of investment, lots of payback, as I've mentioned. I want to thank our partner, Rockwell Automation, and of course my colleagues at PTC. And I look forward to talking to you all about, you know, the amazing opportunities that are available to industrial and manufacturing enterprises thanks to digital transformation. Thank you.